So today, we're very excited to have Professor Kamalika Chaudhuri from UC San Diego as our speaker. Professor Kamalika received her Bachelor of Technology degree in Computer Science Engineering in 2002 from the IIT Campbell, and a PhD in Computer Science from UC Berkeley in 2007. After a postdoc stint at UC San Diego, she joined the CSE department at the UCSD as an assistant professor in 2010. She received an NSF Career Award in 2013 and a Hillman Faculty Fellowship in 2012. She has served as a program co-chair for ASDAS 2019 and ICML 2019, and this year ICML, right? Let's welcome
this year I'm the general chair.
Oh yeah, general chair. Okay. Okay. The floor is yours. Yeah. Thank you.
Okay. Thank you, Sihang. So what I would be talking about is some work that I've been doing for quite a while in my group at UCSD about some case studies in private data analysis, and this is joint work with my current student Casey Meehan and Khalil Mrini, who is another UCSD student co-advised by my colleague. Okay. So, sorry. Oh, wait a minute. Okay, good. So a lot of data that we do machine learning or data analytics on right now is extremely sensitive data, right? And, these are of different types. So for example, there are medical records of people. Genetic data is, extremely sensitive and people want to do data analysis on it. Companies have a lot of user behavioral data, and an example is search logs by Google, and all of these are highly sensitive data. Okay, and what we would be, and so if you want to do machine learning on this kind of data, what you would like to do is you would like to use some you would like to ensure some level of privacy. And what is the kind of privacy that we will be looking at? So in this talk, what we'll do is we will talk about some privacy solutions for different kinds of these different varieties of sensitive data. And what are the kinds of privacy solution that we will be looking at? So we'll be looking at what is known as the local privacy model. So what is a local privacy model? In a local privacy model, what happens is there is no trusted party who holds the entire data, right? So, an example where there is a trusted party is sensors, where sensors, you trust them, they're going to do the right thing. They collect all the raw data and then they do something with it. Here, that is not the case at all. And this is the case in a lot of realistic settings where you can't, either you can't or you don't really want one party to hold, vast amounts of sensitive data, and just simply because there might be attacks and, people might just break into the data centers and so on and so forth. So you just don't want that to happen. And so what happens is there is no central curator. What happens is you have every user and, the user has their, let's just say local device, which runs some sort of privacy mechanism, which runs some sort of privacy solution. And then after sanitizing or privatizing the data, it is sent over to a centralized, aggregator. And notice here the difference between the trusted curator and this aggregator is that this aggregator is not trusted. So it receives already sanitized data. And then this aggregator uses this kind of, the sanitized inputs that it got to give some output. And the output could be something really complicated. It could be, a very complex neural network classifier. It could be the result of, I don't know, a genome-wide association study, or so it could be something really complicated. And this process could also be, complicated in the sense that this process could also be somewhat interactive. You ask a few users, then you ask some more, and so on and so forth. But this is overall the privacy model. We don't trust the aggregator, and the users themselves send out sanitized values. Okay. So how do we, so, okay, so, this was our framework and the model, but what kind of privacy, right? So what do we mean by, how do we define privacy in this setting? Well, the gold standard for privacy in this kind of, in this kind of what one would call the local setting has been what is known as local differential privacy. And we'll go and look at what it is in a little bit. However, this is not always appropriate, and which is, it's a very good solution, but it's not always appropriate when we talk about all these different kinds of data that we talked about, right? Like, the data is not of one kind. And when we talk about all this context, so what we will do today is we will talk about how we can extend the use of differential privacy or modify local differential privacy to fit two specific use cases that we are very interested in. One is privacy of text and the other is location privacy. So these are the two use cases that we will be talking about today. Okay. Okay, so what is differential privacy? And I think most of in this seminar, I'm sure most people know about what it is, but just to, in a nutshell, this is a notion of inspired by cryptography. It's a notion of privacy which was proposed by Dwork et al. In 2006, and the idea is the following: you have data. And you have, if you have a randomized algorithm that takes in a fair bit of data, and then since it's a randomized algorithm, its output comes from a distribution, right? And what differential privacy says is that if I took Alice out of my data set and if I switched her with Bob, then the output distributions would be quite similar. So whether one person participated in the data set or not would not make a big difference. Okay. So what about differential privacy in the local model? Well, in the local model, things are a little bit different from, what happened in the previous slide. So in the local model, remember what I was, what I was talking about earlier. So you have some users value. This is a sensitive value. It could be their location trajectory and stuff like that. It gets fed into a mechanism, and this mechanism is on the user's device, on their phone or something like that. So it has a mechanism, and this mechanism is a randomized mechanism, right? And it produces some output. So this output is considered locally differentially private, and then this output crosses the privacy barrier. So this output or some function of it is sent over to the aggregator. I send over across the privacy barrier to the aggregator. And what does differential privacy here mean? It means that if I replace the user's value, x, by any other x prime, then the output should not change very much, right? And this is kind of, the analog of taking Alice out and replacing them by Bob, right? So if the user was Bob instead of Alice, then things wouldn't change too much, okay? And so far I've been talking about, not changing too much. What do I precisely mean by the distribution not changing too much? Well, this is kind of the definition. If you have two user values, x and x prime, then for all t, if A is an epsilon differentially private randomized, or epsilon local differentially private randomized algorithm, then the probability that A of x equal to t is within e to the epsilon of the probability that A of x prime is equal to t, right? And yeah, and notice here that, E is a randomized algorithm. So the probability is over the randomization in A, right? A is, it's going to do some, random sampling, add some noise and stuff like that. So this probability is over that randomization of A. And notice that here epsilon is a parameter which measures privacy. So higher epsilon means less privacy. And, if it's epsilon equal to 0, then you can see that both distributions have to be the same, right? So epsilon equal to 0 is very high privacy, but higher epsilon means less privacy. Okay. So what are we going to look at? So our first use case is this kind of local level privacy for documents. Okay, and what we are hoping to, what our task is over here is what we want to do is you have a document X, right? So far we have not been talking about, we haven't said anything about what X is. So X is a document. And what we want to do is we have an algorithm, a mechanism on our side, and this mechanism will output a sanitized representation of the document, right? So you feed X into this mechanism A, you get A of X, and this is a sanitized representation of the document. And, and the sanitized A will satisfy local differential privacy, but then what you are getting out of it is kind of a representation of the document, which we can use for other downstream analysis tasks, okay? Okay, so let me take a quick break to talk a little bit about what I mean by representations, right? So forget about privacy for just a minute. What do I mean by a representation of a document? Well, in machine learning now, or in fact, mostly in natural language processing now, something you could do. So there are these things like these large language models, like, GPT-3 and so on, and which are trained on huge volumes of text. And what you can use these language models to do is you can feed it a document X, and what you would get is a representation of this document, something called f of X. And the main idea somehow is that in this representation space, right, in the space of these embeddings, documents or sentences which are closer in meaning are closer together in the space, right? So this representation space, imagine there's an Euclidean distance in the space, and if you had two documents which were talking about the same thing or which were closer in meaning, roughly they would be closer in this, in this embedding space. So that is, that's kind of the idea, okay? And okay, so now and what we want to do is just somehow do this process privately. Okay, so now we have to talk about privacy in text. So what makes a document sensitive, right? There are it's generally it's actually a very, very complex problem, right? Like what makes a document private, and what about a document could be private or sensitive. So for example, if it's somebody's medical records, and it depends very much on context, right? Like if you have some love letters which are being written by let's just say some people who are a couple of people who are having an affair, well, of course the entire thing is super private. Whereas if you have, other documents, parts of it might be private, things like, names and social security information, some of that might be private. If you have like things like medical records, maybe the symptoms with the disease, that part may not be private, but there might be other details that are private and so on and so forth, right? So it's overall, it is a very, very complex problem. And to be fair, we haven't even started to scratch the surface of it, okay? So previous work, which looked at privacy of natural language, has looked at something which was known as word privacy. So what does word privacy mean? Suppose you have two documents, X and X prime. Then word privacy basically means that A of X should be very close to A of X prime if the documents X and X prime differ by a single word that is close or that is similar in what is called the glove embedding space. So glove embedding is, one of those standard natural language semantic embeddings where the idea is that two words that are similar in meaning or that are used in similar context are close together. So you have two documents, X and X prime. If they are different by a single word that is close in the space, then, they should map, then the output distributions would be the same. So an example why that might make sense is, let's say you are talking about taking a trip to Timbuktu. That is more or less the same as, you are taking a trip to Vancouver, right? Here you are here you are kind of obfuscating some personal information as to where the trip is, but you can get a little bit of a high level information is that people are talking about a trip, okay, or you're talking about travel, right? So this is kind of this is the overall idea, okay. So what are the limitations of word privacy? So one limitation, of course, is that it is not interpretable in the sense that it depends on GLOVE. And on the one hand, it is true that we have these semantic spaces, but these semantic spaces are also quite far from perfect, right? Because they are also trained using large language models. Sometimes they map to similar, sometimes similar words in words that are similar in meaning map to similar things, and sometimes they don't, especially for rare words which may not be involved in a lot of training data. That's also sometimes not the case, right? So that is one limitation. Another limitation is that it may not offer enough privacy, right? So at the word, it gives you privacy at the word level, but it may not offer enough privacy for certain things, okay? And in our work, what we are looking to do is we are looking to expand this notion of privacy into what we call sentence privacy, okay? So here, what we do is we look at a document, which is a finite sequence of sentences. And we say that two documents are indistinguishable if they differ in a single sentence. Okay, so if one sentence in the document changes. And now what we will try to do is, instead of word privacy, we will look at sentence privacy, and we will try to implement sentence privacy. Okay. So to implement sentence privacy, we want to find this kind of representation of a document which satisfies sentence privacy, right? So there are two main questions we should look at. So first of all, what is the output space? And secondly, what is the mechanism, right? Like, how do we sample from this mechanism? Okay. So for the output space, what we would be looking to do is we would be looking to generate a task agnostic output space. So the idea is that we won't know what we are doing with the document before we generate the embedding. And the reason why we are interested in this kind of thing is we can use this embedding. So we transfer the embedding over, and then we can use this kind of embedding to make multiple kinds of inferences. Okay. Okay. So what is the kind of embedding that we are looking at? So it turns out in NLP, one of these sort of popular general purpose embeddings that people use is something called a sentence mean embedding. So what is a sentence mean embedding? You take a document, you take each of its sentences, you run them through some, large encoder, and you have their representation in the representation space. And then what you do is the representation for your document is the mean of the representations for each of these sentences. Okay, so this is, without privacy, this is something that, this is a kind of representation that people look to find. Okay. And what we will, so our output space is now these document embeddings, right? And now what we want to do is we want to find a private approximation to the sentence mean embedding, right? So that is kind of our goal. Okay. So what is the first thing that we would think about doing? Well, the very baseline mechanism, and it ties into one of the basic mechanisms for differential privacy, is we would add noise to each dimension, right? So you have your, you calculate the mean embedding of the documents, right? Of the document, right? The non-private sentence mean embedding, and then you add noise to every direction. Okay. The problem with that is that this would result in too much noise and too little utility. And particularly because the diameter of the embedding space is quite high, right? And, the diameter of the embedding space in a lot of like realistic settings, it's not under our control. You are training this really complex neural network. It's generating some embedding, and you can't really always go, you can't really control its diameter, right? So this is out of our control. And so this becomes a bit of a problem. Okay. So our idea is to is instead of adding noise to every kind of coordinate of the sentence mean embedding, we try to do something else, which is we try to use similar public documents as candidates, right? So what will happen is that we will have a bunch of public documents as candidates, and we don't need any labels because it's all because it's we are just it's an unsupervised problem. So we have a bunch of public documents which are candidates, and then we construct our private mean embedding as a function of these candidates. And why would we expect this to help? Well, we expect it to help because it doesn't destroy the structure in the public documents, right? So a public document, if you look at the representation of a public document, it still retains a fair bit of structure. Language has a lot of structure, and the embedding of a public document still retains a lot of structure. And if we can, somehow represent our private document as some combination of public documents, then we don't end up destroying this kind of structure inherent in the language. Okay. So this is kind of our overall idea. We embed the public documents using this, using this embedding function that we have. Then we generate sentence embeddings for our document, right? We have generated the sentence embeddings, and then we privately select an approximation to the mean of these sentence embeddings. So we could have released the mean of these sentence embeddings, but then the entire thing would be not private. Now what we are doing is privately select one of these candidate public documents as an approximation, okay? So this is the problem. Oh, I see some stuff in the chat. Sorry, let me look. I see, excellent question. So, okay, so let me take a couple of questions. So Birhanu is asking, in sentence privacy, what are your assumptions about the relationship or dependency among sentences in a document? That is an excellent question. For now, what we are assuming is that they are sort of independent, right? So one sentence does not leak information about another, but that is definitely something we want to address. And, actually our next use case looks at addressing some of, not in the context of sentences, but looks at addressing some of these correlations. And Said is asking if the embeddings are themselves trained on public data. Yes, that is true. So the embeddings, what we are using is, we can't even train the embeddings ourselves because, we academics don't have that much resources. So we are just downloading a model from the internet and using, yeah. And hoping people who train the model did the right thing.
Makes sense.
Okay. Okay, so private mean approximation. So in the private mean approximation, we are faced with the following problem, right? So we have a whole bunch of points, S1 to Sk. So these are the embeddings of the sentences, and we have a bunch of candidates, F1 to Fk, right? So these are kind of the public, the representations of the public document. And what we want to do is we want to find a private approximation to the mean of S1 to Sk. Okay, so if we were to do the mean, then it would be much harder, but it turns out there is something else that we could do, is we could pick the Fi that privately maximizes something called the Tukey depth. Right, so Tukey depth is, kind of this following quantity in statistics, where the idea is to find a hyperplane such that if you have a whole bunch of points, the idea is to find a hyperplane so that the points on either side are evenly split, right? So moving on to the next slide. So this is, so if you look at the picture down below, so this is the idea. So the blue point here is the point with the maximum Tukey depth, and you can see the hyperplane through it. On one side, there are 4 points, and on the other side, there are 3 points, right? So they're very evenly split. Whereas if you had a hyperplane where on the one side, there was 1 point and, the other side, there was 6, the Tukey depth of that would be 1, right? So, so that would be something with low Tukey depth, right? So why do we care about Tukey depth? One reason is that the point with the highest Tukey depth is in some sense, in one dimension, it would be the median, right? In some sense, this is like a d-dimensional approximation of like a high dimensional median, right? Statistically, that's kind of what it is, okay? And then the other reason we really care about Tukey depth is, unlike the mean, changing one of these sentence embeddings will change the Tukey depth of any Fi by at most 1. And now all the privacy people are happy, because what this means is that this thing is relatively easier to privately approximate. Unlike the mean, where you have to add noise proportional to the, to the diameter, here things are much easier. Okay. So, so now we know what to do. So this is our problem. We can use the exponential mechanism, which is kind of a standard mechanism due to McSherry and Talwar, to pick the Fi, and that privately approximates the point with the maximum Tukey depth. So that's kind of what we do. Okay. So what does this look like? So I'm just giving you like a quick idea as to what the Tukey depth, if you sample from this distribution, what does the distribution look like? So if you look at the picture on the right, the light blue points are the least dense, have the ones that are the least density, whereas, the green points are the most likely ones. And the red points are the sentence embeddings. Light blue points are the document embeddings that are far, that are most, that are least dense, and then the green points are the ones that you are most likely to sample. So so you are sampling at least something close, at least geometrically it makes sense for reasonable distributions. So you might run into trouble, by the way, if your distributions are very bimodal and things like that. But if your geometry is, if your distribution is reasonable, then you will be okay with this kind of thing. Okay, so then this is our overview of the algorithm. You embed your public documents, you generated the sentence embeddings, and then privately approximate them through one of the public documents. Okay. Okay, so now how does this work? And what we did was that we looked at two general, two kinds of document embeddings, and then we looked at downstream tasks. Right, and the downstream task that we looked at was topic classification. Okay, and here are the two baselines. So one is, of course, the word privacy mechanism, which gives you weaker privacy for the same epsilon. And then we also looked at sentence privacy with additive noise, where the noise has to be proportional to the diameter. And the data sets, well, we have more in the paper, but the data sets that I'm showing you now are the Goodreads data set, where we are trying to do 4-way topic classification of book reviews, and 20 news groups, where we are trying to do 9-way topic classification of like news articles. And one thing to kind of keep in mind is that these will be classification done on the embeddings. And when we did the embeddings, we had no idea about the classification task. So we didn't know what we were doing before we did the embedding. Okay, and here are some results. Here we are sweeping from epsilon. In the x-axis we have epsilon, and in the y-axis we have F1 score on the test set. So the green line is, of course, non-private. The non-private is pretty high. The red line is if you just did a random guess, because it's like a 9-way classification or 4-way classification. If you did a random guess, this is what you would get. And then the pink is metric DP is the word privacy one. And the orange line is if you added noise proportional to each dimension. And the blue line is ours. So what you can see is that at least for low-ish privacy, the blue line seems to be doing much better than the pink, even though here epsilon doesn't mean the same thing, right? Like epsilon for the pink means something weaker than epsilon for the blue. It seems to be doing better. And again, here what we are doing is on the x-axis, we have the number of sentences in a document. So as you can expect with these kinds of things, if you have more sentences in the document, the quality of your embedding would go up, right? But quality of privacy would go up since you are ensuring sentence privacy. And again, what we find is that that is definitely happening. As you get more and more sentences, the quality of sentence privacy seems to be going up. The accuracy seems to be going up. And so the takeaways is that, we get something which is a little bit more stronger than word privacy. And it's a little bit more interpretable because we don't have to rely on the glove embedding. And, and we also managed to have pretty decent utility in the sense that, and this is possible because, in NLP, normally, these representations themselves are pretty high dimensions, have high dimensions, and these embedding spaces have large diameters. So candidate selection seems to be a promising alternative in this case. Okay, let me check the questions on chat. Emily is asking. So Emily is asking, what does epsilon measure in the context of your two key sentence privacy mechanism? Is it Yes, it's absolutely comparable to epsilon in epsilon DP. The semantic is a little bit different because, in DP, there is, you have this unit of, what is, what are neighbors, right? So in sentence privacy, it's essentially two documents are considered neighbors if they differ in a single sentence. And what you are ensuring is that the mechanism when applied onto these two neighbors will be indistinguishable. That's the idea. Okay, thank you. Okay, so any more questions on the language part? So if not, I'll move on to the next.
Yeah, I have a quick question. So you didn't talk at all about how do you get this this set of public documents, and I'm assuming they do influence the performance that you're getting.
Absolutely. Absolutely, that is an excellent question. So what we did was we took the same data set for these experiments. We took the same data set and we kept a holdout part of them as the public, right? Like, so we said, okay, half of this data set, imagine this is public, the other half is private. And I absolutely agree with you that this is not something that people would do in practice. And but unfortunately in the privacy literature, most of the work that I have seen is like this. And and this is a direction that we are also actively working on, right? Like to make sure that we can actually have different public and private distributions.
I mean, in my intuition is the closest your public documents are your private documents, the more performance you get out of it, right? That's something that you'd say that's true, right?
Absolutely, yes.
So you'd want a way of maybe like querying and getting like a private Google query that gets you good documents for what you want to embed.
Correct. Absolutely correct. Yeah.
Thank you.
Thank you. Okay, that's an excellent question. I also see something on chat. Let me check. Sorry, I have to click on it to check. How many public documents did we need to ensure that the document embedding space? That is a very good question. So Vishnu is asking how many public documents do we need to ensure that the document embedding space is adequately represented? I don't remember what we used in our experiments. If I recall correctly, we did a 50-50 split, but I'll have to check and get back to you. I don't exactly remember how many what we used, but I think it was comparable. And the second question is, can we have the same set of public documents for different kinds of private documents, right? So there is kind of, so what you're asking is, could there be a distribution shift among them? And again, that is an absolutely excellent question. We haven't looked into that, but I think that is, that is really the open question in this area, one of the open questions in this area. Thank you. Okay, so, sorry, I always have to, sorry guys, I have to just click. Oh, thank you. Okay, thanks. Okay, okay, thanks. Okay, so now that we have talked about privacy of text, now we can move to our second use case, which is location privacy. Okay. So in the beginning, we started out by talking about differential privacy, and what we have been talking about so far has been a modification of differential privacy to sentence differential privacy, right? But it turns out that there is actually another style of rigorous privacy guarantees. This is something that we call inferential privacy. And it was, it's been something that people have been using for a while, somewhat informally, people had been using for a very long time. Even before differential privacy, in fact, people had been using it, but somewhat informally, without rigorous models and frameworks. And it was formalized very nicely by a paper by Kiefer and Machanavajala. And a lot of people have, worked on some form of it or the other. I mean, including, I think, Pratik and perhaps a bunch of people in the audience have also worked on it in some form or the other. So what is inferential privacy? Inferential privacy defines privacy in the following way, right? So what it says is that, so suppose you have an adversary who has some prior knowledge about the data, right? He has some auxiliary knowledge about the data. And then this adversary sees a private release. Well, based on this private release, what happens is they end up updating their posterior. And basically what inferential privacy says is that this posterior should be more or less the same as the prior. So an adversary who has extra information, they should not be able to learn a lot more once they see the private release. Okay, and what we will look at next is a local inferential privacy model. Okay. So what is the privacy problem that we are looking at? So here what is happening is that we are given a sensitive location trace. So this in the picture on the left, there's an example of such a trace where somebody is making their, and this is actually a real trace which was extracted from there's a New York City taxi cabs data set, which, the New York City decided to release a lot of the trajectories of various taxi cabs. And what happened was that this caused a bit of a privacy furor, because you could, because some people immediately worked, they got to work and they could figure out the routes that certain celebrities took, and, where did so-and-so get picked up, and then they went to their boyfriend's place, and, so it caused a bit of a newspaper, so some stuff was in the newspapers and so on. So this is from this data set. So what happens is that you have a sensitive location trace like this, and your goal is to find a sanitized location trace. And where by sanitization, I mean, what I mean is that you get privacy up to a certain radius. Okay, so here, what are the challenges? Well, this problem has a couple of features that we don't always see in typical differential privacy problems. So one feature that it has is the spatial aspect, right? You could give, here, what you could do is, if you wanted to do differential privacy, if you wanted to make everybody's location indistinguishable with everybody else's location, there's no utility that you would get, right? Because, my location is California would be completely indistinguishable from the audience's location in Princeton. And so that, so you want, there's a spatial aspect, and you want to give privacy up to a certain radius, right? Like maybe up to the city level or neighborhood level. Where you are hiding the fact that somebody is at a building or is some block, but you are hiding somebody's address, but you are not, but you are revealing something like, where they are. And then the second aspect, which is also relevant for something like a location trace, is the temporal part, right? Suppose I tell you where I am right now. You could probably predict with high probability where I will be in 2 minutes from now, right? And that is an aspect, that is an additional aspect, which is actually, relevant for privacy, right? Which becomes relevant for privacy in this kind of setting. Okay. So what are some plausible solutions that we can look at? Okay, the first plausible solution would be to look at local differential privacy. And here what you would be saying is that any two people's traces would be completely indistinguishable, right? So, I go from my home to work in California would be indistinguishable from you go from your home to work in Princeton. And that, as you can imagine, would destroy all utility. Okay. So here you are not taking speciality into account, you are taking correlation. So what happened in this solution? You took speciality into did not take speciality into account, right? You didn't offer privacy up to a certain case, was worst case. You did take correlation into account, but the utility that you got was really low. Okay. The second solution is, so this is something called geo-indistinguishability, and this was introduced in 2013 by a group of folks. And here, what they were looking to be fair, what they were looking to do is they were looking to release single locations, where locations within a distance of r would be, a certain distance r would be indistinguishable, right? And so one of the solutions that you could do is you could ensure geo-indistinguishability for each individual location at each time point, right? And this does take spatiality into account, but again, this doesn't take correlation into account, because then what might happen if I was in the same place for, let's say, an hour, and you released my location, 5 minutes, somebody could average it and get a very accurate, picture of where I was, okay? And what we do is a solution which is somewhere in between. So we use something called Gaussian process priors to explicitly model the kind of correlations. And, it's not a perfect model, but, it's some way of modeling the amount of correlation. And then we offer privacy against these class of Gaussian process priors. And so we do take spatiality into account because, through Gaussian processes, we can look at locations and uncertainties around them. We do take some amount of correlation into account. Worst case correlation, we can't do anything, but we do take some amount of correlation into account. And so we have moderate utility, right? So this is a point in this kind of privacy utility trade-off curve. But, but the notion of privacy is a little bit different, okay? Okay, so what is conditional inferential privacy? So to define conditional inferential privacy, we will be building on, so there's a pufferfish framework by Kiefer and Machanava for inferential privacy. This is the KM12 2012 paper. So we will be building on this paper. And, again, this is not the only way to look at inferential privacy. Quite a few groups have looked at, different aspects of it, including actually Pratik's group have, and the modeling differs slightly in every case, but essentially that's kind of what we'll be building on, okay? So what is happening here? Well, imagine we have the location trace of a user, x1 to x1 to x capital T. And this conditional inferential privacy framework will involve 3 components, right? So the first component is something called the basic secret. So what is a basic secret? It's something like the following. User is at, this person whose trace we are talking about, they're at location, a specific location at a specific time, right? So let's just say I'm at home in 10 a.m., okay? Then we will have something called compound secrets, which might be combinations of basic secrets that we are trying to protect. So for example, I am at home at 10 a.m. and then instead of going to a meeting, I skipped the meeting and went to a coffee shop at 10:05, right? So that could be a compound secret. And then finally, we have the notion of secret pairs. So secret pairs are going to be a subset of C cross C, right? Like subset of all pairs of compound secrets. And these secret pairs, in some sense, these are the things that we are, we want to make sure that the adversary can't tell between, right? So for example, one kind of privacy we might want is the adversary can't tell whether I was at home at 10 or if I was, somewhere else in the neighborhood at 10, right? Or maybe the adversary can't tell which building in campus I was in at 10 a.m., right? So maybe the distinguishing pairs could be I was in the CSC building at 10 a.m. versus I was in the, bioinformatics building next door at 10 a.m., something like that, right? This would be, so this is kind of the idea behind secret pairs, okay? And then finally, what we have is a set of conditional priors. And in our case, this would be a set of Gaussian processes. So because we are using Gaussian processes to model these location trajectories. And here is our definition of conditional inferential privacy. We say that the mechanism M obeys PR theta, conditional inferential privacy, with parameters lambda and epsilon, if for all priors theta in theta, so for all Gaussian processes in our set of priors, and for all secret pairs, right, Si and Sj, in this pair of secrets, right? What we have is that the Rene divergence between the two distributions, right? The conditional distribution, so the distribution of the outputs conditioned on the secret being Si versus the distribution of the outputs conditioned on the secret being Sj, right? So these are two distributions. The Rene divergence between these two distributions is at most epsilon. So there's a couple of things to slightly unpack here, right? So let me try to point out some differences with the differential privacy definition that we had talked about earlier. So one is that here, so it's similar in the sense that, you can think about Z as being the output of the mechanism. And, remember we talked about all S and S prime. So you can think about this as being, all Si and Sj, right? But there are two subtle differences. So one difference is that now the randomness is not just over the noise that is added by the mechanism, but it is also over theta, right? So, and theta is somehow reflecting the adversary's uncertainty, right? So the adversary, so the randomness is not just over the mechanism, the noise added by the mechanism, but it's also over the adversary's uncertainty. So this is one difference. The second difference is now we are talking about, instead of how we had this kind of pointwise ratio, right? What we had before is that the ratio that A of x equal to t versus A of x prime equal to t, for every t, that ratio was at most e to the epsilon. So instead of, this level of, so this would be something like the max divergence between these two distributions would be at most epsilon. Now, instead of max, we have relaxed it to Rene divergences. And the reason why we did this, people have actually done that for other kinds of privacy, for differential privacy, for example. But the reason why we did this relaxation is because Rene divergence goes beautifully with Gaussians. And looking at Rene instead of max lets us design, nice Gaussian process mechanisms, which are actually nicely computationally tractable. So that's why we did this relax. So those are the two changes, and that's kind of why we did them. Okay. So what can you say about this kind of thing? So one thing that we can say is that it's robustness to prior misspecification. So if your prior is completely off, well, of course, there's nothing you can say. But if your prior is off by a little bit, then what you learn is also off by a little bit. So it's not just, so there's a graceful degradation as your prior moves away from the prior that the privacy mechanism was designed against. Your knowledge also changes a little bit. It doesn't change a lot, right? There's a graceful degradation. You also have graceful composition in time, which is similar to parallel composition, which is, an excellent property that differential privacy has. And then, what about mechanisms? So the first baseline mechanism that one would think of in this case is that you add uniform Gaussian noise to every time point after calibrating the standard deviation to ensure enough privacy. So you could always do that. But it turns out in our framework, you can also write down the privacy loss for releasing a trace Z given an input X, and you can minimize the mean squared error. And because of the magic of Rene divergences and Gaussian processes, this can be done by a semi-definite program. So this can be, okay, I should say approximately done by a semi-definite program. And this is kind of the magic. And I'll end with some experiments. Here, what we are looking at is on the x-axis. So we try to make this as interpretable as we could. So on the x-axis, what we have is different kinds of prior, right? So this is on the GeoLife data set. And on the x-axis, we have the prior dependence. And on the y-axis, we have the adversary's confidence interval length, right? So the adversary looks at, has some prior, looks at the private release, combines it together to form, a posterior, and then it looks at the confidence interval, right? And if you look at the confidence interval length And then if your confidence interval length is larger, that means the adversary is more unsure about, where you are, right? So large confidence intervals is good. And then as you go along the x-axis, what happens is your prior encodes higher and higher dependence. So your prior encodes higher and higher dependence between the data points. Okay, and so what you see over here is that, and here again, the blue line is our mechanism, the semi-definite mechanism, whereas the orange line is the baseline that we had talked about, right? And what we see over here is that the semi-definite mechanism, the SDP mechanism, seems to do better than, has higher confidence length, so the people are more uncertain than the independent uniform. And I must also say that both have been calibrated to the same utility, right? So for the same utility, our mechanism gives us higher privacy loss. And here the privacy loss is measured the same way. But if you use our mechanism for the same utility, you would get higher privacy or lower privacy loss than for the independent Gaussian mechanism. Okay. So this is the these are the experiments. So in conclusion, we looked at new local privacy solutions which go beyond local differential privacy, and for specific use cases, which were more use case specific, more flexible, and went beyond local DP. And what we got was mechanisms with better and more fine-grained privacy utility trade-offs than LDP and and geo-indistinguishability. And so these are our two references. So the first is a paper in ACL this year, and the second is a paper we had at AI Stats last year. And finally, I'll just end with the picture of the two people who did most of the work, and I'll take your questions.
Okay, great. Thanks for the talk. Do you guys have any questions? Just feel free to unmute yourself. No question. Yeah. If you have questions, just feel free to unmute yourself, or you can also type in the chat.
I had a question. So your mechanism, does it take the actual prior distribution as input, or is it that it just takes the class as input? Because I saw there was theta in capital theta.
Right. It takes, so this specific mechanism, it takes a specific theta, and that theta was here, that theta was calculated over a held out data set.
I see.
In this specific case, kind of, these are different people's trajectories. You fit a Gaussian process model to the average trajectory of a held out data set, and then you.
I see. So if you want to make a specific user trajectory of user private, you have to know some information about their private, like how do they move in general, and then use that.
Exactly. How do people generally move? Yeah.
How do people generally move, or how that a specific person?
Oh, no. How do people generally move? These are different users. So when I said I held out data set, what I mean is, so the GeoLive data set has a lot of user trajectories, and we took half of the trajectories as a holdout set, and then the other half, like different sets of users. Yeah.
I see. Okay.
Yeah.
Thanks.
So I have one question related to this last part, which is, so does the method generalize to other domains where the conditional priors may be different, or the set of secrets could be unique? Right?
That is an excellent question. The mechanism, so the method, like the privacy modeling, yes. The mechanism is very tied to Gaussian processes and Renyi divergence.
I see. Yeah.
So if you can,
that's what I figured out as well. Yeah. Otherwise, I guess, I couldn't really see how you can untangle it from the Gaussian process and think applying this for another domain, maybe.
I see. Yeah. So there's something you might want to see is that we had another paper in the pufferfish setting, but for the not the local model, for the global model in 2017. So there we look at more, somewhat more general dependencies.
Sure, thanks.
So maybe that might be. Or yeah, so here it's very much tied to the Gaussian processes. Yes.
Sure. Thank you very much.
Cool. Is there any other questions? Okay, I think maybe that's all for today. Let's thanks again, Professor Kamalika for the great talk, and also thanks everyone for this great questions.
Yes, and thank you. Yes, thank you everybody for the great questions, and it was very nice seeing some of you. I know. Okay, thanks.
Thank you.
Okay.
Bye.
Hey, bye, and see you guys next week.